Welcome friends. In Sanjoy Nath's Geometrifying Trigonometry, the first mission is to convert any trigonometry expression into its Euclidean geometry, the kind of geometry that you can assume in Euclidean geometry. You all know that trigonometry deals with triangles, and in every expression, whatever the trigonometry expression that we see in our textbooks, those are coming from any survey problems or any bridge design problems or from any kind of height and distance problems. You know that very well, that when you are doing any height and distance problems, before solving the problems you draw the pictures, and then after some calculations and after observing the pictures that you have already drawn on your page or paper with the pen and pencil, then you try to find the triangles and then you try to relate the line segments. Ultimately, trigonometry deal with three kind of things: line segments, angles and triangles. But what do you mean when you solve any trigonometry expression, or what do you mean when you try to equate left hand side expression with the right hand side expression? You don't know every time, I think so. So you have never asked these questions to anyone, that what is the geometry, what is the Euclidean geometry hidden inside the expressions. Suppose you have given any trigonometry expression or any identity on the left hand side and on the right hand side, then the left hand side should represent some line segment and right hand side totally represent some other line segment, and both of these line segments should have same length, or these two line segments should overlap on each other. It can happen that left side is representing some angle value and right side is representing some angle value, and they are numerically same. Sometimes in some identity, the identities are also invariants if that is occurring everywhere for any value of angle theta or alpha beta or the things involved in the expression. For any values of those cases, the identities are always invariant, and invariant is a very important subject in any kind of mathematical understandings, for abstractions or for the topological problems or in geometric problems or in any kind of equation kind of things. When we equate anything, first we evaluate things and then we try to prove some properties. Sometimes you will see that on the left hand side of the expression there are some ratio, and on the right hand side of the expression there is another ratio. When the ratio is there, that means when the two ratios are equal in any expression, that means it is talking a story about the two similar triangles. We know from the property of similar triangles that the left hand side is the ratio of two line segments, that is the ratio of the lengths of two line segments, and that is equal to the ratio of corresponding line segments of some other similar triangle. That is the basic idea. Whatever the triangle looks like, either it is the right angle triangle or scalene triangle or equilateral triangle or isosceles triangle, and that doesn't matter. Main thing is that when there is any ratio on the left hand side and another ratio on the right hand side, that simply means the expression, that is the equality, is trying to represent the story of two similar triangles. The top for every ratio has a numerator and a denominator. So left hand side also have a numerator and a denominator, and on the right hand side also there is some numerator and denominator. In Sanjoy Nath Geometrifying Trigonometry, it is discussed as the numerator is the output line segment and whose length is taken, and in the denominator, that is the input line segment whose length is taken. And in case of the ratios, we can't guarantee that every time the initial line segment is the input line segment. Sometimes due to some Gtsimplex effects, the output line segment of any Gtsimplex is taken as the input and output line segment of any GT segment is taken as the output. So any ratio we can think it as not as a number, but the Gtsimplex divided by Gtsimplex is equal to another Gtsimplex divided by another Gtsimplex. So Gtsimplex is like a number, but it's not number actually. It is a conglomerate group. On the right hand side you can see a large number of line segments, and every line segment has some name, and with every of these names are started with L, you can see. So at every stage of this construction, one Gtsimplex is constructed, and I will explain you how these Gtsimplexes are constructed, and as a whole the whole things come out. And these kind of expressions are Gtsimplexes, and it can take many kind of shapes when theta is changing, when the seed angle, the theta is the seed angle taken here, and when theta is changing you can see the dynamic effect of the changing Gtsimplexes, and I will explain it slowly later on. But let me explain the concept of divisions of Gtsimplexes, additions of Gtsimplexes, multiplication of Gtsimplexes, subtraction, plus minus into divide. All of these things are well defined. Equality is well defined. Ultimately Gtsimplex is a group of points, line segments and triangles. Ultimately those are the glued forms of triangles, and when theta varies its picture changes. Even the expression, trigonometry expression remains same, its picture changes. And stage-wise construction of the Gtsimplex is also shown here, and this simulator you will get for free in Autodesk forum if you search it with automated trigonometry. If you search in Google with automated trigonometry, you will get this simulator for free in Autodesk forum, because this is supported with Autodesk analysis and researches, and several people from Autodesk specialized teams have tested on this, and they have verified several list programs when these things were developed. And Sanjoy Nath was developing these kind of things. He was working with the Autodesk people to get it verified. The outputs are verified, and several contributors were working on the list programs, and then ultimately Sanjoy Nath has developed this C# module such that anyone can pull this project from the exe directly, referencing to in their own programs, so that they can get the Gtsimplex data, and for doing their own machine learning modules to generate their own theorems with the automated trigonometry proofs, and conjecture designing, or to formal proof making with TensorFlow learning systems. And with the machine learning we can generate many kind of theorems, and we can verify theorems also. Those are all the big plans with which we can proceed. But first of all, we should understand what is Gtsimplex and how Gtsimplexes look like. And Gtsimplexes all have a common line segment, which is taken as the initial line segment, which is called L as per the conventions of geometrifying trigonometry. Now this we were talking about the plus minus into divide. Plus minus into divide are all done through the output line segments of Gtsimplex. Every Gtsimplex has an initial line segment, and after the trigonometry expression is worked out on the given line segment, due to the algorithms of Sanjoy Nath's geometrifying trigonometry, the whole algorithm is inbuilt inside this exe file, and you can call that as a reference from any other exe or any other DLL, and you can get the effects. You can get the outputs there also, and you will get the text files which you can use as the learning sets for machine learning, such that you can design your own theorems, you can verify your own theorems, and you can also proceed with the additional features of the symmetry calculations also. And this is the starting point to work out. Now Gtsimplex's output line segments are added, and when any output line segment is moved on the 2D plane, we have to move the whole group of Gtsimplex together with that line segment, and wherever the output line segment is moved on the 2D plane, the whole Gtsimplex moves with that. Any of the line segment we can move on the 2D plane, like the lifting and shifting of the vector algebra. The same kind of thing that we can do on any line segments of Gtsimplex, but the condition is that the moment you are moving the line segment, any of the line segment, it is locked, self-locked, and so whole Gtsimplex will move together. In the same way, after the addition is done with the output line segments, and many Gtsimplexes are placed one after another, and keeping all the output line segments aligned one after another, then also it becomes locked, and so the whole output becomes a locked set. Suppose you have an infinite series, and suppose you have a power series or any kind of series. Every term is a Gtsimplex, and all these Gtsimplex terms have the common initial line segment L. All of these terms are generated from the single line segment L, single given line segment L, and every of these terms have the different Gtsimplexes. But how can we add these different Gtsimplexes? Just by lifting and shifting the Gtsimplexes such that the every output line segments of every Gtsimplex in a power series can get aligned in cumulative way, or can get aligned forcefully in a linear way. We can do any of these things, and sometimes you can see that naturally all of these line segments are getting in a single line one after another, and those are called natural summability of power series. Those are natural summability of the power series. Now let us explain how to run this software and how to visualize the Gtsimplexes. It comes out with many kind of invariance analysis, and so we can visualize many kind of such things like bounding boxes of every Gtsimplexes, and we can stop these bounding boxes such that the jungles can get removed, so that we can test the simplest views of Gtsimplexes. It automatically saves the file in bitmaps, and also it saves the file to the scale in DXF file format in your D drive. And if the D drive is not there in your system, then this will generate the Geometrifying trigonometry folder at the location where this exe is kept. Now we will show the lesser jungles so that we can check the Gtsimplexes only. We will not check other behaviors of summation of output line segments. We will talk about those things later on. Now we can talk about these things here. The initial line segment L is the first line segment. Its length is taken as 1000 millimeter here, and this is the AAPB, automated, zoomed and scaled to fit in this way. This is the GT string, that is the command string. This is the GT string, the Geometrifying trigonometry string. How should we interpret these kind of strings? It's very easy. In the forum from where you will download this exe, there it is already explained that L is the initial given line segment. A, B, C, D are the four types of symmetries to construct cos theta. E, F, G, H are four types of symmetries to construct sin theta. I, J, K, M are four symmetries to construct tan theta. We, in this simple simulator, we have kept only one theta, only one seed angle value, and such that all the triangles can become similar triangles. We can take different values of theta for different ratios, alpha, beta, gamma, in that way, and the varying values. We can do that also for different multiplicative models. And Gtsimplex are the multiplicative terms. Every terms are multiplicated somehow, and in that case only we will call it the Gtsimplex. Otherwise we will not call it a Gtsimplex normally. Any triangle is also, any single triangle is also a Gtsimplex. It is the simplest form of Gtsimplex. But until the simplexes are glued like this, like at every stage the gluing is added. Suppose if we change the theta, then you can see the behaviors of this gluing. Stage wise the gluing of new triangles are coming, and one more line segment is added, and one more alphabet is added. With that, for example, suppose this is the given line segment. This one is the LA, this one is the LAO, this one is the LAOA, this line segment is the LAOAO. In this way, one additional triangles will add, and in that way it forms this whole Gtsimplex, and ultimately there is a final output line segments if we take it a small value, L A A A O O O I I I A A A Z Z Z, in this way if we take it, then we can see the behavior is changing. And for the different values of theta, we can see the different kind of symmetries coming out of this. And all these things are Gtsimplexes, and every of these Gtsimplexes have a unique behavior for every different values of theta. So you can see that how the line segments are added and conglomerated together as the stages are increased. Suppose the construction stages are increasing in this way, and it flips at a certain point because the symmetry value is taken in that way. I will explain all these things. A, B, C, D, E, F, G, H, I, J, K, M are already explained. N, O, P, Q are the four symmetries of sec theta. R, S, T, U are four symmetries of cosec theta, and V, W, X, Y are four symmetries of cot theta. So, and Z is the final output line segment that represents the final output line segment, where Z is written, that is the final output line segment. And for every Gtsimplex, one initial line segment is given, and obviously there is a final output line segment, and you can see that there is a final output line segments. And at every stage, suppose here LA, LAA, LA is A, all these things have a different output line segment. Suppose up to this the output line segment is A, up to this the output line segment is also AA, up to this the output line segment is LAAA, 3 times. L is starting, it is common for every time. And if I take here I, J, K, I in that way, then the picture will change and its behavior will change. You will see that its behavior will change, and new kind of patterns will come out. If you don't want these jungles of the address of the line segments, then you can put N here so that the texts will not be shown here. You can see the text values for each values, the texts are shown here. Now on the address lines, every line segment has an address, and if you want to stop those texts to come here, then you can put N, and then the address of these line segments will not come. Then you can visualize the Gtsimplexes only, and you can check the beauty of these Gtsimplexes. And the texts are of the two types: the output line segment address texts and complement line segment address texts. One thing in our previous videos also I have said, for every multiplication with any trigonometry ratio, we take one initial line segment and two line segments are taken. Suppose if L is multiplied with cos theta, then we take L as the hypotenuse, and that cos theta decides that L is taken as the hypotenuse, and the base object, base line segment is generated, that is the output. But you cannot complete the lines triangle until the complement line segment, that is the sin theta, is also generated. So the triangle is complete now. First Gtsimplex is generated. So this, when cos theta is multiplied with L, output is cos theta, that is the base, and perpendicular is the complement line segment. But in case if L is multiplied with sin theta, then output is sin theta, which is perpendicular, and complement is the base. From this you can understand the properties of the Gtsimplexes is always having a output line segment or one complement line segment generated due to multiplication with any trigonometry ratio. That is the fundamental basis of Sanjoy Nath's geometrifying trigonometry. That is, the construction protocol is explained in this way. Now we will try to show you the basic cubic natures of cos theta or cos cube theta. Or first let's try to explain you the cos square theta, the behaviors of cos square theta, and we can explain the behaviors of sin square theta. Now cos square theta can take 16 kind of symmetric behaviors. 16 kind of line segments are possible due to cos square theta. How? We were trying to explain this here. We should show these output line segments at least the output line segments at least, such that we can explain these things easily. Suppose here we are taking LAAZ, which means LAAZ is the output line segment here, that is cos square theta. LABZ, we have already said that ABCD are 4 symmetries of cos theta. So we can think that for different values of theta, we can see that LAB, the line segment, this one is the LAB, and if we get the construction sequences, then this one is the L, and for the smaller value of theta, for different values of the theta, suppose this one is the theta, I can change it from here also, say 26 degree, then this one is the base, that is the LA, and this one is the LAB. Of one more triangle is glued, where this one is the common line segment. In the same way, LACZ is also another kind of cos square theta, which we can check like this, that is the LACZ. LADZ is also a kind of cos square theta, where if we take the values of the theta differently, then we can see the behavior of the output of LADZ. So this one is the LADZ here. In that way, in the same way, LAEZ is also cos theta into sin theta. In that case, LAEZ is the cos theta into sin theta, and LEAZ has a different behavior. I want to show it here. LEAZ has a different behavior, and first also it will do the sin theta, then it will take the cos theta, so its behavior will change. LAEZ and LEAZ are not same thing. This is Gtsimplex, and you can see the gluing behavior. First triangle is drawn, then another triangle is glued with that, and the output is coming here. In the same way, if we take the cos square theta sin theta, LAAEZ, then we can see that it looks like this, and stage wise we can think of it as LA, LAA, LAE. This line segment is generated now for different values of theta, say 30 degree. It will take its behavior differently. Say it is 15 degree, then its behavior will change in this way. This one is the LAAE. In the same way, LAAFZ will have different line segment as the output. Here say it is the 26 degree, then its behavior is LAFZ is this one. This is the color of the output line segment here. LAFZ, LAAFZ. In the same way, we can think of, suppose we should explain you the Gtsimplexes of cos square theta and Gtsimplexes of sin square theta. LAAZ is the behavior of cos square theta. LABZ is also cos square theta. It is also cos square theta. For any value of theta, we can test it through sliding here, and it can help you to visualize the nature of dynamic geometry, that how the property of this whole arrangement of Gtsimplex changes if we change the value of theta. The theta is seed angle here, and several calculations are already shown, simulated at the same time when we are changing anything. That is the beauty of any dynamic geometry systems. Now LACZ is also another symmetric behavior of cos square theta. LACZ. This is made with C#. Some of the graphics options were tested before with the Java, and I made the Java API also, but that is not released yet. Now LACZ, LADZ is also one variety of cos square theta. In the same way, you can play with the suppose this one is the LADZ, this is the LADZ when it is 62 degrees. Suppose we are trying to do LDAZ, then you can check the behaviors of non-commutativity. Every of these multiplication are non-commutative. LDAZ is here, not here. That was LADZ was here and LDAZ is here. In the same way, LAAZ, LABZ, LACZ, LADZ, LBAZ, LBZ, LBCZ, LBDZ, LCAZ, LCBZ, LCCZ, LCDZ, all are also cos square theta. In the same way, LDAZ, LDBZ, LDCZ, LDDZ are also cos square theta. Now if you want to see how it should look like LAAC, CCA, AAC, CCA, Z, that is how many characters are there? It is showing there are 13 characters, slider value 13, which means cos to the power 13 theta. It is showing the cos to the power 13 theta, and we can see its behavior like this. Now I want to show you another interesting magic here, that is the if all the output line segments of the stages, suppose the stages are like this. First one is the LAZ, then LAA. You can check the string, you can check the string from here also, and the how many degrees taken, it is also showing here. You can reduce the degree to 16 degree or any bigger degree like this. LAAZ, then one stage is added LAAC, LAAC. In this way, one additional cos theta is multiplied and its behavior is changing. We know that the cos theta and sec theta is 1. I have already said that sec theta is NOPQ. If we take LANBO CP and DAQQZ, that is the cos to the power cos and sine are in cos and sec are multiplied. NOPQ are sec theta, and ABCD are cos theta. So after multiplying, we should get a 1 as the output. So the output line segment has the same length as the input line segment for this Gtsimplex, and we can check the behavior of this Gtsimplex for different values of theta. And the behavior of this Gtsimplex is like this, and it is a jungle. But you can see that for very different kind of angles, some of the line segments are parallel, some of the triangles are equal, some of the parallelograms are forming at different kind of values of theta, and you can see that for some special angles you can expect there are different properties. Suppose if we take it as a 45 degree, then its behavior changes. For 11 degree, its behavior is different. And now we want to see the behavior of the summation of the output line segments. At every stage of the construction, we will see that the outputs are different. This one is the output of first summation in the first stage of the construction. second one is again overlapped here, then third one is over generated. In this way the output line segments are added one after another. We want to see the behavior of the summations of these cumulative summations, the forced summation of the output line segments one after another. Then if we want to see the cumulative outputs here, then this blue line is formed, and if you want to see the cumulative summation of the complement line segments, then a red line construction is formed, and we can see the behavior of this summation of every stages are taking interesting behaviors. These blue lines are the summation of output line segments, and these red lines, red thick lines, are the summation of complement line segments. And you can see that at every stage of the construction from this slider we can change the construction construction sequences. First LA is taken, then LAN is taken, then LNANB is taken, and at every stages the output line segments are cumulated, and then also parallelly the cumulative sum of the complement line segments are also taken. And in this way we will see the behaviors of the Gtsimplexes. We can check many different kind of Gtsimplexes here, any different kind of combinations we can check. AO, 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 CN, 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 CN. This has a value of 1 because the final output line segment will have the same length as the initial line segment, because A, B, C, D are cos theta, N, O, P, Q are sec theta. A into O means cos theta into sec theta, again multiplied with cos theta, again multiplied with sec theta, again multiplied with cos theta, again multiplied with sec theta. In that way C is also cos theta, N is sec theta. In such cases we can see for different values of options we will see the different kind of dynamic geometry. And if we stop the texts here, if we stop our texts here, then we can see it more cleaner. The Gtsimplex is here, and its summation, the output line segments cumulative summation, looks like this. It's so beautiful, and I have not shown the Gtsimplexes with every output line segments. That would make it more jungle, but the data sets are prepared and such that you can train TensorFlow models with that. With the different values of theta, you can see that the summation of output line segments are changing, and that's the beauty of this dynamic geometry systems. And at every stages you can see that for different values of theta, the dynamic natures of this whole Gtsimplex is changing, and parallelly we are showing the summation natures of the output line segments. And you have never thought that cos to the power n theta into sec to the power n theta can have such beautiful Gtsimplexes. I want to show you one interesting thing here. I want to show you a very interesting thing here. Suppose if we stop the summation, if we stop the summation here, then it will do some beautiful outputs like this. And if we check the constructions, if we check the constructions for this output, suppose say it is the angle is initial line segment is taken as, say here 26, it is like this. For 30 it is like this, and for 45 degree it looks like this. Say we take it 22, and then we can see this kind of thing. Here several line segments are parallel to some other line segments, and this whole thing is the Gtsimplex. When I have stopped the summation effects, then the scale to fit, automated scale to fit, is taking the zoomed effect. The zoom to fit is done here. Now we can check the stage wise constructions. First construction is done in this way, second is this, third, the fifth, sixth, eighth, 10th, every alphabets are added, multiplied, and then it suddenly changed its direction because the different symmetries are multiplied now. And you have now understood, I think, the multiplication with cos theta and multiplication with sec theta has a different kind of geometric behavior that you have never seen in your trigonometry books. Suppose it is in the 60 degree or 63 degree, then you can understand it better. You will get more beauty with the offsetting. Suppose we are trying to understand the construction stages. These are the gluing, again gluing, again gluing, again gluing. The different triangles are glued, and after gluing we will see that different kind of pictures are forming, and the swapping of the triangles, all are the similar triangles you have noticed here, because all of these are making a 63 degree seed angles. So all of these triangles are all similar. These pictures of Gtsimplex are generated just because different symmetries are multiplied one after another, and you have also understood the multiplication is non-commutative. So every permutation will give us different picture for a single value of seed angle. Every permutation will give us different picture. So it's a huge subject, and we can expect a chaotic situation, and sometimes we can see that all of these line segments, all of these output line segments for every permutation carries same information. That is like quantum entanglement, which says that information is carried by multiple things at the same time. Why not? All of these are symmetric output of all of these permutations of multiplication are actually same thing. All of these are representing the same Gtsimplex. So we can confidently say the entanglement problem, the EPR paradox, is not the problem of physics. It's the problem of symmetry, and we are not taking care of all kinds of symmetry while solving algebraic expression. If we solve every problems with geometry, then we will get the secrets of entanglement. The entanglement is not a very big deal, because all of these different pictures, entirely different pictures, are having same trigonometry expression, and all of these are forming entirely different Gtsimplexes. That is the fundamental claim of geometrifying trigonometry, and it is showing in front of you, and you can construct all these things with ruler, compass and protractor on your page. This software is just to simulate, to show the process. You can do it yourself with pen and paper also. It is so open, clean sheet to everyone. It is open thing, and anyone who knows how to construct geometry, how to construct similar triangles one after another, anyone can construct these pictures. You can see. Only the thing is that you have to take care of every kind of symmetries, and think that every trigonometry ratio multiplies to generate 4 symmetries. Every addition generates 4 symmetries. All plus minus into divide, everything has a quad tree. So you cannot expect that only one answer will come. Cos alpha into sin alpha is not same as sin alpha into cos alpha. Cos alpha and sin alpha multiplied to generate 16 different arrangements, and that is for one side. And if we take sin alpha into cos alpha, then again there are 16 different arrangements, because cos alpha into sin alpha is not same as sin alpha into cos alpha. Some of the Gtsimplexes so formed due to cos alpha into sin alpha will give the same Gtsimplex as sin alpha into cos alpha. Those special cases are theorems in geometrifying trigonometry, and you can find such a large number of theorems, and several of such theorems are not so easy to find without machine learning systems. So we all should try to prepare data with these kind of simulators, and then we have to train any machine learning platform, and from that we can generate many theorems, and which can change the face of electronic industry also, and from several of such theorems someday we will get the understanding of EPR paradox also. And we claim here that several entanglements are not actually a puzzle. If a same expression can have 64 different right pictures, then all of these 64 things are entangled, we can think, because every of these corresponding line segments are carrying same information every time. Whatever the angle it is carrying same information. So entangled is not a puzzle, it is quite natural. If we try to solve things geometrically, then the entangled problem is natural. It is not anyhow puzzling thing. We are trying to solve things with complex numbers, or we are trying to solve things with algebraic equation, and that is not exposing all four symmetries at every stage of plus, minus, into, divide. For that reason, entangled cases are looking like puzzles. Thank you.